An impedance converter gyrator circuit with two op-amps and transformer shown. We want to see what is Z or input impedance observed from port 1. Assume that op-amps are properly biased so that they are in linear region of operation, they are not saturated. Therefore, virtual short is valid, meaning that the positive input terminal and negative input terminal for each op-amp, they have the same voltage. So here we have a transformer with 1 to n turn ratio from port 1 to port 2 of transformer. On one side, you have a capacitor connected. On the other side, we have voltage V2. Since voltage V2 is assumed there with current I2, V2 should be at positive terminal and also should be at negative terminal as well because of virtual short. So we have V2 on both positive and negative terminal. Now you can see for R and alpha R, they have V2 on one side and they share a node on the other side. So the voltage drop across alpha R and R is the same. As a result of that, if current I2 comes in that cannot go through the positive input terminal because it has infinite impedance and has to go purely through alpha R, this I2, if it goes through alpha R, we can easily see that the current that goes through R should be alpha I2. Because then alpha I2 times R equal to I2 times alpha R, so the voltage drop across two resistors would be the same as they are supposed to be. This alpha I2 has to go through R on top as shown. So it goes like this. And the voltage drop across R in addition to V2 will result in Vx, voltage at this node. So I can write Vx is simply equal to R alpha I2 plus V2. Okay, that's helpful. The other thing I can, so let's keep that. That's equation number 1. That is helpful and useful. So let's keep that. Okay, so this is equation number 1. Now, the other thing that I observe is, if this is Vx, again, the virtual short is valid for this second op-amp. And as a result, if Vx is here, Vx should be here as well at the positive input terminal. Now, as a result, there is this current flowing through this resistor toward ground. So that current, obviously, Ix, is equal to Vx over R. This current has to go through horizontal R as well, so it has to go this way. Now, the resistor R here and the resistor R here, on one side they have a common node, they share a node, and the other side they both have Vx. So the voltage drop across these two resistors is the same. Therefore, if Ix is flowing through this one, Ix has to flow through this one as well. So Ix goes this way. And since this Ix cannot go through the input terminal of ideal op-amp, it has to go up. So what goes up is Ix. And we know Ix is Vx over R. So I'm going to write this. I know Ix is Vx over R, or let's say Vx is simply R times Ix. Okay, this is equation 2. Now let's combine these two equations. So equation 2. Let's combine these two. And if we combine, we can see that as a result, Rix equal to alpha Ri2 plus V2, and then as a result we get Ix equal to alpha I2 plus V2 over R. So this is equation number 3. Now at this node X, write a KCL. You can see from what is written here that I1 is simply alpha I2 that is flowing outward. So this alpha I2 that is going out minus Ix. So, and you can see that's exactly what we have here. So if you write this in the form of Ix minus alpha I2, so take alpha I2 to the other side, to the left side. On the right side, you have V2 over R. And on this side, Ix minus alpha I2 is Ix minus alpha I2 is simply I1. So there you go. So what I arrive at is I1 is V2 over R. That's very interesting. So current at this port in this scheme or setup is just function of V2 over R, as we saw here. Now, okay, let me also write this, that V1, the voltage at this port, obviously is Vx, and then voltage drop across R. So if we are defining like this, we can just say it this way. V1 is Ri1 plus Vx. Okay, if that is the case, then one mistake I did is in this scenario, Ix minus alpha I2 is actually negative I1. So I need to be very careful about that. So it's basically, as a result, what I get is this one. So I1 is, with this direction that is defined here, is negative V2 over R. Reason for that is obvious. Ix plus, at this node, if you write a KCL, what you get, I'm just going to write it here, you get I1 with this direction that is defined here, plus Ix is equal to alpha I2. So as a result, what you get is, if this is what you are looking for, then Ix minus alpha I2 is equal to negative I1. And hence, this is negative I1. And as a result, I1 is negative V2 over R. So just a clarification quickly. Okay, so that's a KCL, obviously. And what I need to do is, as a next step, I need to just say V1 is Ri1 plus Vx. So V1 is Ri1 plus Vx. Now let's substitute I1 from here. So we have, um, if you substitute that, what we get, V1 is Vx effectively, and I1 is negative V2 over R, so become Vx minus V2. That's what we get. Now, what I can do is, I can substitute Vx from equation 1. So here what I used is equation 3, if it helps, 4. So just as a reference, so that there is no confusion, here what I did, I use equation 4, substituting I1 with minus V2 over R, and then R and R cancel out, and then this Ri1 becomes Vx, becomes negative V2. So this whole thing is Vx negative V2, as I have written. But now I'm going to use equation 1 as shown, and Vx is R alpha I2 plus V2. And at the same time, we have negative V2. So these two obviously cancel out. So as a result, what I get is V1 is equal to R alpha I2. So V1 is equal to, let me write it this way. So therefore, I get V1 is R alpha I2, or if you like to write it the other way, I2 is equal to V1 divided by alpha R. That's very interesting. So that is the exact equation we see in a gyrator circuit, in which the current at one port is depending on voltage on the other port and vice versa. So effectively, if with these two equations, if you combine 5 and 4, so if you combine 4 and 5, and if you just out of interest, just write it in matrix form, you can see that we are saying I1, I2 equal to, and let's say on the other side we keep V1 and V2 as a column matrix, you can see that I1 only has dependency on V2 with a ratio, with a coefficient of negative 1 over R. So it's as if it doesn't have any dependency on V1, but then negative 1 over R. And then I2 has only dependency on V1 with a coefficient of 1 over alpha R. So we have 1 over alpha R, and then we have 0. So this is the classical two-port impedance matrix representation or admittance matrix representation. So this is our current matrix, and this is this one that is written here, this one is our admittance matrix by, and this one is the input voltages at the ports. So the the classical representation of two ports, this is effectively two ports. One port on this side, one port on the other side. So for V2I2 related to V1I1, effectively what I'm saying is I am representing in the form of I matrix equal to admittance matrix Y and then times V voltage vectors. And as you can see, the admittance matrix is this matrix that shows that port 1 has dependency on for the current at port 1, it has dependency on voltage at port 2 and vice versa. This is what is referred to as gyrator. So this admittance matrix is admittance matrix of a gyrator. Basically, a gyrator is a circuit that has this sort of a 4 and 5. Um, so these are indicating that we are dealing with a gyrator. Okay, and with that in mind, um, what the last thing I need to do is just one last step. I am going to write Zn. So Zn is equal to the one that I wanted to find. Obviously, is V1 divided by I1. So we have V1 divided by I1. And then for V1, I am going to use I2 times alpha R. So 5, using 5. V1 is alpha R times I2. Great. For I1, I am going to use number 4. So using 4, I get I1 is negative V2 over R. Okay, great. So what did I get? I get negative and then alpha R squared times I2 over V2. That's what I got. Okay, so what next? So as you can see, I have a simple circuit here. There is a current that is going through the on the first side of this transformer. I have a current IC with this direction that is going through the cap to generate the voltage VC, and obviously VC is just current IC times the impedance of cap, which is 1 over CS. That's the relationship between current and voltage of cap in S domain. And if we wanted to see what is the voltage V2, given that we have an ideal transformer with 1 to n turn ratio here, the voltage will be n times VC. So because of the transformer that we have, so ideal transformer with n turn ratio, it's an ideal transformer, indicates that these relationships indicates that V2 is n times, let's say, VC, voltage on the other side, and I2 with the direction that is shown. So I2 is equal to negative because by nature current wants to go this way, generate a voltage like this, but the direction of I2, as we have indicated, is countering that, so we have a negative sign because of that. I2 is then negative 1 over n, the relationship enforced by the ideal transformer, times IC. Okay, I am going to substitute these relationships. Using these relationships, I'm going to substitute for V2 and I2. So negative alpha R squared times I2 is minus 1 over n IC minus 1 over n IC divided by V2 is n times VC. Okay, so negative counteract this negative, so I get alpha, and then I have R square over n square. And finally, I have IC over VC. But IC over VC, as we can see here, is simply CS, because IC over VC is the admittance of capacitor, which is CS. So it's going to be CS. So at the end, what I obtained finally is Z in, as observed from port 1, is equal to this outcome. And that's very interesting because Z in feels like an impedance. That's the lesson. It feels like an inductance. That's what I learned here. So you can see that we have a constant. Of course, it's a function of parameters in this circuit, including the value of alpha in this potentiometer or variable resistor, the R itself, the number of turns in this ideal transformer, and then the value of this cap C. But at the end, alpha R squared divided by N squared times C becomes effectively my L. And the way Z feels, Zn, is as if it feels like an inductor because it's Ls as long as this circuit is stable, of course. So the art is designing and selecting parameters and keeping the circuit stable for a range of L that can be realized with this circuit. But we have a good degree of freedom in terms of L being controlled by a bunch of parameters. I hope that this example of illustrating the usefulness of gyrator combined with, say, an ideal transformer to convert a capacitance to inductance is helpful.